So here we are back in the video and we were talking about attention mask, right? So let's see what are attention mask. For that, we have to move just a bit ahead. Okay, so what we are going to do now, we are going to tokenize the whole data set, then we will see that what is attention mask. Okay. The DistilBERT cannot work with the whole lines or text input in each row. So it's important to tokenize each of the rows of the data set, right? So I created a custom function which can tokenize each row of the given batch of the rows. Basically, dataset, right? This will return tokenized batch text padding true and truncation true. What is this padding true and what is this truncation true? Let's see. Okay. The above custom function has been defined so a dataset like emotion can be tokenized on each of the train, validation, and test dataset. Okay. So now by this method, each of this test, train, and validation dataset of the emotion dataset will get tokenized. Emotions.reset format. Okay. Now, firstly, that we have. Previously we set the format of the emotions to pandas, right? Now we need to reset the format to default, right? Because the pandas has a different data types of data frames, we cannot work with that, so we need to reset the format. Now emotions, now what will we do? We will get the encoded data set by this line of code. Emotions encoded is equal to emotion.map tokenize batch true batch size none, right? Now, okay, continue GPU, right? So emotions encoded we have, let's see how the encoding has been done. Okay, so we will just like how the dataset will be look like when it is encoded with to the whole emotions, like to the numbers format, right? Name tokenize is not defined, tokenizer. Okay, so I guess I didn't run this code. Now let's run this code. So it is mapping each of the encoding to it, right? So emotions encoded has been done. It has created encoding for each of the row of the dataset. Okay, let's see how the encoding has been done. Okay, now what I will do, I will access. We are accessing the encoding done on the train dataset, training part of the dataset, right? Now let's see that how the encoding train data frame looks like, right? So we have this is the text and these are the input IDs and this is the attention mask. Okay, now what is happening here? Let us try to understand it, right? Okay, so how will it look like better? Yeah, it is such messed up. Oh, right, very good. See, this is the text. I didn't feel humiliated. And then this is the associated label that is 0, right? Now this is being encoded into the input IDs. Firstly, it started with 101 and it ended with 102. Now what are these zeros after it? What are the zeros? And we have this attention mask. We have 1, 2, 3, 4, 5, 6, 7. 7, 1, and then rest of them are 0. See, 1, 2, 3, 4, 5, 6, 7. We have 7 non-zero input IDs and then we have 7 non-zero attention masks. What is it that when we work with a data set, okay, see, this is a small sentence and then this is a very large sentence. And then there may be some even larger sentences. Now, it is important to maintain the number of inputs and the number of input IDs into one of the row IDs. For example, like if some text creates 50 tokens, so its input ID will have 50 digits, right? No, sorry, 50 numbers. Okay, but another text that this text got converted into just you can say 7 numbers, right? So now it's very important. So it is very important for the matrix format that it will also be in the format of 50 numbers. So what will it do? It will create the input IDs for the first 7 numbers, and the rest of it will keep as 0. And by the attention mask, the transformer will understand, okay, for this first 7 I have to take them as the numbers, but rest of them are, I don't have to do anything, they are meaningless, they are just for that. So that actually what happens in a transformer, these all numbers will go into the matrix format, and matrix, we need to maintain the size of the matrix. So that is the reason that it must each of the row must contain the same number of numbers, right? So the meaningful numbers will get mapped to 1, other all to 0. So that is what attention mark shows, that what are the meaningful numbers and what are non-meaningful. Okay, great. So encoding train data frame, I just want to see the input IDs and attention mask. I have just explained you that what is it and why is it used. Okay. By the way, I just created this head. Okay, so this head, what does it do? It will only give us the first 5 rows of the dataset, right? Great, cool. Now we have done we have loaded the dataset. We are done tokenizing it. Now what we are going to do? We are going to train the text classifier. Now see, where is the diagram? See, this part till this hidden state had already been trained by the BERT, by the people who developed BERT, the people who developed the DistilBERT, and that is the file that we downloaded here. That the DistilBERT, that model CKPT file had the weights of already downloaded. It was a file that had the stored weights for the pre-trained model, right? But this classifier header has not been trained because it was trained for the masked language modeling and the next sentence prediction. It was not trained for this classifier head. So now we have to train the classifier head. Till then the model will work by itself. It will convert each of the sentences to these hidden states. Now we have to train it. Okay, so these are the hidden states. If these are the hidden states, then this is the label. Okay, for the train data set, we have 16,000 rows. We will tell it, okay, for these 16,000 rows, these are the particular labels. Now for the next text that we are going to give you, you need to find what is the relationship between them, so that you will classify into a particular class. Okay, that's how we are gonna train that's why we need to train the classifier head, right? Where is it? Okay, yes. So we are going to train the text classifier. So there are two ways of classifying text. First is feature-based extraction, and next is fine-tuning. Feature-based extraction is the type of class training that I just told you, that we already are relying on the pre-trained model. We are relying on the pre-trained model to give us this hidden state, and then we are just training it to classify it to a particular class. But what in the fine tuning, what happens? We fine tune this whole pre-trained model, these whole pre-trained weights, to make the hidden states like as if we are going to classify it into multiple classes. Okay, so what is the problem that we'll see ahead? That why do we need this whole training why do we need to train this whole DistilBERT again if it has already been trained to these hidden states, right? So firstly, we are going to see feature-based extraction. Okay, so using pre-trained features, let's use the pre-trained weights of the model, and by using an auto class from Hugging Face transformer, namely auto model using .pretrained. Okay, so we are importing the PyTorch, library, checking the version. We are importing the auto tokenizer, right? Because no, sorry, we are not importing the auto tokenizer. We are importing the auto model, right? Particular model which is associated with a DistilBERT base case. Okay, so now, and we are loading the particular weights of the model, right? Now, what is a device agnostic code? Okay, so a model will use GPU if it is available. Otherwise, it will run on CPU, right? Why? Because GPU is always better because GPU has higher memory. Sorry, GPU can work with more type of data. Okay, so it will see right now I have connected into T4 GPU, right? So it will use GPU, and if it is not GPU, then it will work on CPU. Okay, that is your device. Because when we are working with PyTorch, PyTorch works with arrays. Okay, so let me write it here somewhere. PyTorch works with arrays, and it is very important for the arrays to be on the same device. For example, for array A plus B is equals to C, formation, A and B need to be both on GPU or on the same CPU. All right. That is why defining the device is very important. So we use this model to load the pre-trained model from model CKPT file, this model CKPT file, and it is being sent to the device, this device that we have here, right? Let's run it. Okay, so this is the torch version, PyTorch version that we are using. Now, since this model will get loaded, now what we will need, we will need to extract the last hidden states. The last hidden states are the digits, are the numbers that it has produced by analyzing all of our data. Okay, for each text it will produce a last hidden states, and we will train it that what hidden state. Okay, so this is the hidden state for the first sentence. You need to associate it with the surprise. This is the second hidden state. You need to load it. You need to associate it with a joy. Okay, so for because of that we need to extract the last hidden state. So let's firstly do one thing. I am using some custom text, and then I'm going to associate, I'm going to analyze, I'm going to see the hidden, I'm going to extract the last hidden state for each of these texts. Then we will extract the last hidden state for all the data of the dataset, right? This is the first text, example first text, and then we have this, which is example second text, right? Okay, and then in this line of code, these are being put in a list. Okay, so firstly what I will do, I will tokenize it, each of the text, then I will put it in the encoder, then the transformer will give us the last hidden state of each of these text. Okay, so inputs, tokenizers. Okay, so what in this line of code, what is happening, each of the text is being converted into tokens, yeah, that's what is happening here. Padding true and truncation true, so it will have the right matrix shape. These are the inputs. Okay, so this is the first text, and then this is the second text. As you can see, the attention mask are in the same format. These are rest 0, and these in this all are 1, right? Okay, so now what is the shape? We can say that I passed the torch, I passed the two texts. So we have 2 batch size, and then we have 12 number of tokens for each of it. Okay, so these are 12 tokens, 1 2 3 4 5 6 7 8 9 10 11 12. Okay, for first text only 6 were needed, but 6 are more added to match it with the shape of the next text, right? Now in this code, what we are doing, we are sending, it's not sending but storing each of the PyTorch arrays. Sorry, it was not array. These are called tensors actually. PyTorch tensors. storing each of the tensors into the device defined earlier. Okay, and then what is this with torch no grad? Now what we are going to do, what we are going to doing with this particular line of codes, we are trying to find the output of this input. These are the input, these are the encoding inputs that are going to be fed into the transformer, and then what will it produce? It will produce a last hidden state, right? So these are the input that I produce, these are the inputs that I set up. Now I will put it inside the model. What is model? This is the model. Where is it? This is the model. This is the model, right? This is the transformer model. Okay. So what is this torch node at? If you have studied about the gradient descent, then actually whenever we feed some input inside some model, it has a bad habit of always producing calculating the descent, the gradient of each of the inputs, when we pass into some models, so that it can use it later for the gradient descent purpose. But that's only necessary when we are training. But this time we are not training. We want to get the output. We want to get the last hidden states. Okay, this will avoid the gradient calculation, right? Then we will get the outputs that are the last hidden states, and then we will print these outputs. Okay, these are the outputs, right?